All right, class, we have one more itsy bitsy thing to do in 4.2, which is we're trying to get a numerical value for how much variation there is. So whenever we talk about variation, we kind of want to have a number. And what happens in stats, it just becomes a percentage. But there's 15% of variation here. There's 28% of variation here. So it becomes a percentage of how much variation is happening. And real quick here, and we'll be done. Just one quick formula, and we're good. So what's the formula? It's called coefficient of variation, CD. Kind of funny. In math, we usually just use one variable, right? One letter to represent variables. In this case, we have two, a C and a V. But still, it's the same. It's just a variable. Okay, describe the standard variation of a data set as a percentage of the mean. So how much standard deviation is there of the mean? It looks like this right here. For a population, CV is equal to that S over there, Greek letter, it means standard deviation, divided by A. Anybody know what that letter is in Greek? Not paying attention. Not sigma. Ooh, sigma is the top one. Very good. The bottom one is called mu. It's like M and a U mixed together. Kind of looks like it, doesn't it? Doesn't it look like an M and a U kind of like got married or something? Okay, so mu, sigma over mu times 100%. And that's given as percent. How about this sample set? What does sample set mean? Same exact formula. In this case, it's just the English letter S. And it's the X with the bar on top of it, which means the average. That's it. So given as a percent. That's cool, yo. Okay, we're good. We get 10 from which is fast. All right, I'll just keep on going. Boom, here it is. Here's our little data set just to say it. So this is heights of and weights of a basketball team. So first things first for you guys is it a population or a sample? Population. Population. It says so. Okay, so we have how many players are on the basketball team? There are 12 players on the basketball team, right? So we look at their heights and look at their weights. And the question really is, how much spread is there in the heights of these basketball players and how much spread in their weights? Which ones has more spread? Which one has more variation? Let's jam with it here. So if you were to go back and you look at the height, just the heights, I'm not going to make you calculate it with a calculator, we'll go a little faster. If you just look at the height on a, I found out that the mu is 72.8 inches. Also, I calculated, remember standard deviation? Does it take a little bit of time to calculate standard deviation, or does it take a lot of time to calculate standard deviation? It takes a long time, right? Remember that? It takes a tremendous amount of time. So I'm going to give it to you. So can you guys find the coefficient of variation for the height? All yours. Just label it as CV. Use those little numbers right there. So CV, put like a little H next to it, or if you want to write it out, you put CV with a little tiny, it's called a subscript. So you put H if you like, or just height and stuff. Okay, real quick here, you guys should be able to do it yourself. It's a population. You can use the population formula. You have the variables in front of you, and anybody give you the answer when you're done. Yeah, everybody's doing the calculator out now. All right, good, good. Yep, Brian, go ahead.
0.0453.
0.453. That's cool. Except now we got to change it to a percent. Perfecto, I got it. Yeah, maybe like nearest 10%. So here's our whole formula. What we do is we go 3.3 divided by 72.8, multiply by 100, and voila. Yeah, good. Sweet. Okay, 4.5. 4.5% is again the amount of variation that's here, right? Cool. Let's do the other one over here. Got to give you the numbers for that one. All right, tell me if I'm going too fast. Good. Good. Okay. This one, all yours. Mu is this. The division is that. All yours to get that one over here. Compare notes. And the round off to the nearest 10. You got it, and the answer is 9.4-ish. You got it. And we have ourselves about 9.4, and then the final answer. Final answer is this. Let's compare the two. So the weights, 9.4, are more variable than the heights, right? There's more variation in the weights of the basketball players than there's the heights, either the heights are more closer together. Pretty tall people. Comparing variation. You're comparing which one has. Okay, are we good there? Can we switch gears then? Let me go to close this off. Jump to this one, and the last section of the day. Here it is. 5.4 measures of position. Now the question is this: where are you in the data? Well, where is stuff in the data? Ready? Let's jam. So first things first is we're going to learn about something called quartiles. So let's jam to this here. So we have something called fractals. So let's kind of set this up. Fractals just means that numbers are divided into a certain ordered set, into equal parts. And so fractals kind of like fractions, right? And the first one that we're going to study, and the one that we're going to take the most amount of time studying. So this is one type of fractal, right? One type of way to divide ordered pair into groups or stuff. So one way is to do it by quartiles. So you're dividing the group into 4 different equal parts. And what are they? Q. We might as well use a letter. We'll call it Q1, the first quartile of Q1. And roughly a quarter of the data falls on or below Q1. We're going to get to Q2. And this one's going to be about half of the data falls on Q2 or lower, and sometimes called the median. Hey, we heard of that median before. And then quartile 3. So about 3/4 of the data fall on or below. It's called a quartile system. Lots of writing here. This is probably the most amount of writing on the slide. Close. One more slide. Less than half done writing, so go for it. It's not me going as fast as I can. This is fast. Quartile left. Are people still writing? All right, let's jam. And again, if you want me to go back to the slide during break, please do ask and we'll go for it. So let's try a data set here. A little more writing here, not all of this, but maybe just kind of put down automobile commuters. Maybe example 1. So just automobile or waste fuel. So each year in the US, automobile commuters waste fuel due to traffic congestion. What do you get rid of traffic? Anybody live in a very, very congested traffic city? LA, oh yeah. My nephew used to live in LA. On a, without any traffic, you can get to work in about 20 minutes. With traffic, hour and a half. There's fun stuff there. Large cities have the pluses and minuses. Small cities have the pluses and minuses. Okay, so this is wasted by commuters in the 15 largest U.S. urban cities listed. So the first, second, and third quartiles of data that are given. And so my question is, what do we observe? So let's do this here. Can we, first of all, write these guys in order? Once we write these guys in order, can you give me the median? Give me the median value. Anybody tell me what is the median value? Where we start with stuff down. So write this down in order, and then you give me the median value. Down, that's awesome. Down order now. Good job doing so. Now the question is, can you give me the middle number? 49. Okay, so I'll go with that. Just tell me if you guys agree. Is there only 125 or well, there's 325s? 325s and the last 25 is so let's see, can we start this as well? So quarter 2 is going to divide the data into 2 equal halves. So notice what happens here is we have found this guy here. So it looks like since there's 15 data points, right? That means there should be 7 to the left side of the median and 7 to the right side of the median. And so that little guy there, there's our Q2. So label it as Q2. That was sweet. Awesome. Okay, everything there. 25. 7 on one side, 7 on the other. Because it was an odd number, we know we had to find a median, right? Okay, now it's I kind of gave it away because it's darker here. So now let's go on to the left side of the median. Can you find the median of those guys? Pretty easy because it's bold already. 23, and then we say that is Q1. That's cool. Then we jump to the other side of 25 and we look at those 7 entries there and we get the middle of this guy and wow, it's 30. We're going to label that as Q3. 8 times after time. Okay, now the question is this: what do we know? From the definition of Q1, what do we know? The amount of gallons per year of fuel wasted, right? By commuters or a quarter, right? A quarter or less is 23 miles per gallon, or just kind of wrote it out here. So here's what, about 1/4 of large urban cities, auto commuters waste 23 gallons of fuel or less. Is this for, this is for a whole year or no? Is this annual or what is it here? Yeah, gallons per year. So it's, guys talk to me, let's see. So 23 bucks, the gas price is about $4-ish. So $4, so about per year in traffic, sitting in traffic. You waste about $100 a year just in fuel. Right. Or at least the dollars. Right. Okay, Q2, about 1.5. Waste 25 gallons or less, we did there. And about 3/4. The top 15 urban cities waste about 30 gallons. Okay, how we get it? There's your P1, P2. Let's jam to. Okay, now we have something called IQR. This is called the inner quartile range. Super duper important. And so now the question comes up with this slow down here. So we want to figure out what is kind of like the middle portion. What's about half of the data we have? Well, hold on. So if Q1 represents 25% and Q3 represents 75%, if I take 75 minus 25, makes 50. So interquartile range is kind of the 50% of the data. It's like the middle 50%. Here, all the data kind of bunches up. The next one, I don't want you to write down because we're actually going to do those. This next slide, let's read it together. I don't have the title's not correct here, but let's kind of read it together first. And actually, I was incorrect. Title should be finding the. Let's not write it down. Don't write stuff down. Just kind of think with me as we go. Okay. So it should be how to find the outlier. Outlier is all the data that's kind of like a little too far away. You know, it's almost like this one little area that's way, way on one side. So how do we do this? What we do is we figure out what Q1 and Q3 are. We figure out the IQR. Multiply the IQR by 1.5. Why 1.5? Because now we're almost, we'll talk about this a little later on here, but we're on the unusual numbers of layers. So we subtract 1Q5 from Q1, and anything that's lower than that, that's an outlier. And then we go the other way. We go 1.5 times IQR, and we add it to Q3. Anything that's higher than that, that's going to be an outlier. Okay. So let's try it. Let's try it. So remember that first set that you guys should have already written down? Can you find for me the interquartile range? And tell me when you found. So now write this down real quick here. So Q1 is 23, we know that. Q3 is 30. So the IQR is going to be 30 minus 23 or 7. There it is. So there's a spread of 7 in the exact middle of the group. Okay, with that said, let's try to identify any outliers. So before we do that, we're going to do one more extra computation. We're going to multiply 1.5 times 7. 1.5 times 7, this is 10.5, that's cool. So again, that gets us into the unusual. So can you guys do this here? Give me the lower. You find the lower. I guess we can go to this here. Lower end would be a Q. Okay, leave it lower. Lower end. It's Q1 minus. Look at this. Brain freeze. Minus 1.5 of the IQ, which is 23. Give me that one. Let me write it on the computer itself, so I can add the later reference. So to find the lower end, we'll usually say Q1 minus 1.5 times the, in this case, 23 minus 10.5. I think I heard something right. Another question is, go back to look at your data set. Erase this. Do we have any data that is less than 12.5? 11, okay. 11 is an outlier. It's just unusual for the number to be there. Good. 11 is an just over here, super quick. Let me do this here. I made a mistake previously, slide over long. Almost. Did you guys find if there are any outliers in the higher end? Outliers there. I'm going to do this real quickly here. Q3 and then add. So we just did this one here. This is to find the lower. Right? We see if there's any lower outliers. This guy will to find out if there's any high outliers. You think we find? So this one, we'll go back to this so I can have slide in order. Some stuff here. Sorry, that's right, slide. Okay, higher end. Q3 plus 1.5 times the height we want, which is, what is Q3? David? Ooh, I think that the answer is up. What's just Q3? 30. And previous stuff, and this is 10.5. And we're 40.5. Question is, do we have any numbers? No, nothing on the higher end. Seems like the data on the higher end is kind of a little bit more clustered together. So no higher end outlier. So 11 is and it's going to affect the data quite a bit. So that city, for some reason, maybe they have better traffic flow, right? It's not usual for that to have. So maybe that's something that other cities can model. Maybe they have certain way that the cities flow. One interesting city is Boston. Anybody live in Boston or had a drive to Boston? Boston is unusual because we don't know where streets came from and why they're there. Boston was one of the most inhabited cities, right, before kind of paved roads came by. So some people said as soon as people start walking in a certain direction, they just made a road. And so sometimes you have roads cross each other in weird angles. Sometimes you have intersection that comes together with 5 lanes. Portland does the same. Portland is the intersection of Portland where there's 5 lanes. Anybody good in Portland do that? Okay, cool. See that. Okay. So weird stuff. There it is. So maybe that one would be an interesting one to look at. Let me give you. Let me give you a picture real quick here of the outlier, right? But guys, give me the section that did mean, median, mode. Which one was that? That did mean, show you the outlier. This was a good one here. Here's your outlier. All right. Notice that little one right over there? It's 65. Age of students in class, right? You have a whole bunch of group of students here. Their ages from 20 to 24, almost exclusively. And then you got the 65-year-old in the class. So if you're going to say, hey, what's the average students here? Or what should we concentrate on, right? And so notice that 65 really just skews the data pretty bad. So if you got rid of that, then you really would cluster the whole group together. Then you kind of know what this is good. So if you're trying to get assistance for students, or you say, you know, pretty much everybody is either like fresh out of high school or a little bit past high school. So then the question is, what kind of help services should we offer, right? What kind of quad activities should we do? Probably not like jumping jacks. Or yeah, probably jumping jacks, right? As opposed to the 65-year-old is not going to be part of it. Okay, does that make sense, you guys? Okay, so let's jump back to 4. Okay, so there it is. Quartile range, you use it to figure out if there's any outliers, any stuff that's really big that is not going to do, we can skew that data. Okay, how do we graph it? We actually have a way to graph this guy. And very technical math name for it. It's called blocks of this. So here's how we graph this whole concept of Q1, Q2, Q3, and the interquartile range. So box and whisker plots, first of all, they are a data analysis tool. Highlights very important features in the data and requires a 5-number summary. This is the next slide. It's probably the longest to write down. And the last slide is so long. All right, always need the 5 numbers. So first one is going to be the minimum entry. What's the lowest number of data you have? Then we're going to plot Q1, plot Q2, plot Q3, and then we're going to drop or graph the highest entry. Based upon that, we have all the numbers, and we also know where they kind of bunch up in the middle. Really quick, used quite a bit. In many, many different platforms here. You guys might have seen it. In Canvas, have you guys ever looked at your grades compared to others in the class? I scored this much, how did the rest of the class score? And you've seen it then. So there's a little dot where you're at, and then the rest of the class are there. Probably more people still. Here. All right, Jam looks like this. Da, da, da. We're good there? So don't need to write it down. We're going to work with it anyways, but just for you guys to see a visual. And notice right in the middle, we give this little box. You make this little box from Q1 to Q3. So don't need to write it down. We're going to work with it anyways right now. We're making one anyways. So notice the minimum. And so yes, the box, why is it called box and whisker? Because box is that little middle, hey, that's the interquartile range, isn't it? Yo, it's been there all this time. Whiskers are the stuff at the end. So can you please, dun, 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 dun. Okay, we'll go through this, da, 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 da. Can you guys make that same little guy for this stuff? The only extra stuff that you want to put down is you want to put like a little number line on the bottom. You want to set a number line on the bottom. Checks. I should have. Before you read it, I'm going to not show you this. Can you put a little number line that shows all the values? What you're doing. Once you do that, you make that. And I'm going to over 11. And here. Okay, let's jam. So hopefully you have some sheets like this. Animate it the way I wanted to do it. Oh, sorry, it should be something like this. Good. So you have, don't forget this little guy here. You have the bar line on the bottom. This one should be very consistent. This is the one that kind of gives you the spread. You want to put these numbers and then space them out pretty evenly as you go. Space them out well. And you want to go, the number line should go a little bit further, reach further beyond. So our minimum is 11, and we're spacing by every 5, and go down to like 10 or 5, maybe even 0 if you want to. 35 is the highest, we went up by 5, so maybe at least go out to 40, maybe 45. Okay, and then put your 4 dots down where you like them, or the 5 dots. Dot your minimum, dot your Q1, dot Q2, Q3, and max. And have you guys seen this in Canvas? Except what happens is they don't have the dots and they just have your dots next to it. Hey, after we take our first exam, we kind of a random student. I don't know. I won't say who it is. That's not cool. So there's your box and just for spot. Half of the data is between 23 and 30. And then, now notice that little 11, notice that little whisker going down. It's way further out than the other one here. So you kind of tell the data out. So that was one. That was one way. This is the quartiles, right? This is the quartile method. And this is graphing of the quartile method. There are others. And so I don't need to write this one down because I think we can just kind of look at it. I think it's like a book as well. So for as far as fractals are concerned, we looked at quartiles just now. There it is, divided into 4 pieces. We also have a decibels method. So divide stuff into 10 pieces. If you can see it, usually it's kind of like for small amount of data. Class. Like. And so, but quartiles are almost used all the time. That's the one that's used the most. Also percentiles. Percentiles are also used most. That's when you have a whole bunch of data points. And what you do is you divide it into 100 pieces and you find out what is your percentile rank. So that's what we do. Okay, but what we are doing all this time is just trying to figure out where you are in the data. That's the whole point. So are you in a 75% category? Or are you the 25% category? That's going to be. So real quick here, let's jam to this one. Don't need to write it down. Just going to give you here. This is SAT scores from the College Board. That's pretty cool. So the question is, where does someone fall in the 80th percentile? So the percentiles are going up. Notice it goes all the way to 100 always, right? And so that little rate from about 800 up to about maybe 1300, that's the biggest change that you have. And then you have a perfect score of 1600 on SAT. Real quick here, out of curiosity, raise your hand if you did take an SAT while you were in high school. You guys came in one day, you like a Saturday morning, right? And you came in and you took like this 4-hour exam. Right? Did you guys know what you were doing? Or you were like, hey, you take this exam, go. Right? Or did you just like study? It was a practice, right? You're supposed to practice before? Cool. Minute, did you do practice or you're like, okay, Saturday you come to a test? Okay, Saturday, okay. And Jacqueline? Saturday test. Here you go, take this test. It is what colleges use to determine if you should Compared to your grades, they look at your grades and they look at your SAT score. That's the same thing you need. Like, hey, tomorrow you have this little test. You come over here. You show up like, oh, okay. All right. So this is kind of cool. So if you remember your SAT score, now you know where you fall, right about there. But notice now it's about position. It's like, hey, what is 80%, or what score do you need to be at the 80% tile of all the scores or lower? That's kind of what you're looking for. All right, so let's do an easier example. Not SAT scores in college, but let's go to this one right here. So how do you find your percentile corresponding to data here? So the percentile that corresponds to a specific data point is X. And it's usually rounded to the nearest whole number, so you're going to do the 99th percentile, 134th percentile. So we get it as a percentile. So formula, you probably want to write down, stuff in red is important. So percentile of X equals number of data entries less than X. So you just count. You count how many data points you have less than the X that you have. You count how many total entries you have. You multiply by 100. Hey, very close, very similar to what we just covered in the beginning of class today, right? Kind of similar to the coefficient of variation, right? But this time we're actually looking at the position. So just count how many less than what you want, divided by the total, multiply by 100, round off to the nearest person. Let's jam with one data point. I'm going to give you the data, but you just look for it here. So this is a sample of data. Tuition costs in thousands of dollars, and I went from the smallest to the largest. So that 16 represents 16,000, 18 represents 18,000, all the way to 52,000. To find the data set of the sample, to find a percentile that 34,000 corresponds to. Think about the previous formula that you just did. How many entries are before the 34? How many entries are there total? Divided by 100, all yours. Go for it. All right, you guys talk to me. How many data points are there that are less than 34? 8. Awesome. Okay, 8 is good. How many data points are there in total? 5. Anybody second at 25? Okay, that's good. So how about 8 over 25 times 100? so I got myself a 32. It's nice. It goes like 33. Sorry, 32 point. It was like 32.4. We still round it off to 32. If it was 32.8, we round up to 33. And what in the world does this mean? Is that particular university corresponds to the 32nd percentile rank, which means 32% of universities cost less, and 68% of the universities cost more. Absolutely, yeah. That was one more formula to do, and we are good to go. Okay, guys, so that's position, that's percentile rank, that's kind of where you're at in the data. But a lot of times when we look at data for statistics, we look at those standard deviations away. Like this stuff here. Let's take a look at that. Right? Some of you are not. Okay, let it at the jam. 32 percentile. This end result is 32nd percentile. That's not the answer. Okay, so the more abstract one that we're actually going to use later on is this one right here. It is called the standard score, and eventually just called the standard Z-score. And it represents the number of standard deviations that X falls away from the mean. So how many standard deviations are you away? Formula is given as the value, which is X minus the mu, which is the mean divided by standard deviation. Very good. Formula down. And so let's just do this one. Last example over here. 3 slides to go. So if you want to write this one down, we're going to compare Z-scores. We're going to compare if a certain person is unusual, usual, and let's see, usual scores, and then very unusual scores. Okay, let's get, and again, this is standard deviations, right? Those are the little standard, 1 standard deviation, 2 standard deviations. So this is what we got. We have men's height and women's height in a population. It's a mu is 69.9 inches. What is that? That's 5 foot, almost 70, right? So that's gonna be 6. So 5'10". So the average man is about 5'10", with a standard deviation of 3 inches in every direction. Women's height 64 inches. What is that? That's going to be 5'11". 5.5? 5.4? 5.4 is the average height for a woman with a standard deviation of 2.6. So there's actually a little bit, tiny bit less variation with women than for men. So can you use the formula that was on the previous slide? Can you compare a 6 foot tall man, and if it's usual for a man to be 6 foot tall, unusual or very much unusual? That's what I see this. All right, can you also do it for a 6 foot tall woman? Yeah. Okay, let's do this. The one thing we should note is 6 feet tall means 72 inches, right? So can you guys use the previous formula? Just use 72 inches as X. So almost done. Last example. Last example. So we'll see it written down the U and the standard deviation. That's good. And I just want to make sure that you got this formula. Did you get this formula? Yes or no? Okay. So the X would be your, for the men, that would be your 72. U would be 69.9, standard deviation would be 3, and just calculate that. Yep, absolutely. Just a second here. No, just your score. It's gonna be a score, and we'll put it on the little scale. U is the average for population. Sorry, ask again. Oh, U and U. Instead of mu, it's just mu. So the M says his name, then you say his name. Okay, Josh, ready to go? Okay, so I'm gonna go here and here. Here is not that one. Here's your height for men, height for women. If you want to just do one of them, that's cool too. If you want to do both, so I'm going to do the men's Z-score and I'm going to do the women's Z-score. We're going to compare Z-scores, and this is used quite a bit. This is probably the one that's used the most. SAT uses percentile for position. Everything else, or a lot of other stuff uses the Z-score. So for the men's score, you should have 70 minus 9.9. Whatever you get for that little number, you can divide by 3. Anybody got that one yet? 0.7. Okay, we'll just kind of leave that there for now. Okay? You guys agree or disagree? Okay. Make sure you disagree. All right, anybody did not get 0.7. That's what I'm going to make sure. Use the calculator just real quick here. Anybody did not get 0.7. If you didn't, most likely you did not put parentheses, or you calculate all at once and you only divided the 6.9 by 4. That's it. Okay, very good.
Oh, yeah, so I have a women's.
Okay, Z-scores, let's do this here. Z-scores are usually rounded off to the 10th place. Sometimes if you want very, very much better, to the 100th place. So, okay, z-score, anybody got z-score for the women's? 2.96, I believe, is that right? Everybody saw yourselves, and I got myself a answer of about 3, so roughly. So notice, funny thing is, notice the equal sign above, and notice the little squiggly equal sign at the bottom, right? Equal sign on top, if it's solid, it means you got the exact answer. Squiggly line means we were rounding off somewhere over there. Very important distinction in mathematics. Very important distinction in math too, in the science. Okay, what in the world does this mean? And so you want to write down the graphic that's on the next slide, and we'll finish off with this. And z-scores, yes, they could be negative as well. So if you get a negative z-score, that means you're just on the lower half, not on the upper half. Okay? So if we were looking at, instead of 72, if we were looking at 62, would actually get a negative z-score, and that's perfectly fine.
Wow.
Or put parentheses. Parentheses, then you keep all that together.
Thank you.
Uh-huh. Tricks of the trade. Okay, real quick here, what does this mean? Graphic on the next slide, here it is. This little graphic right here. So if you want to copy this one down, that's kind of good for you. So we say this, these are z-scores right here. So if you had a z-score of 0, you are right in the middle. If you had a z-score of 0.7, you're about right here, but you're still a usual score. If you get a z-score of 1, still usual. When you get a z-score of 2, you say that's our dividing line right there. 2, that means you are getting into the unusual scores category. And then when you get past 3, then forget it. You are a very, very unusual score. And so this is going to test whether things are really, really far away from the middle or close to the middle. In fact, chapters 6, 7, 8, 9, and 10, that's what we're going to be doing. We're good? So super duper important here. Just this whole concept in your brain as we finish up with statistics, right? Descriptive statistics. We're going to take a break. For the next 3 chapters, we're going to do probability, which may have include stuff like this. This could be a different subject altogether. They don't confuse the two. We're going to take a big old break from stats. We cover probability for the next 3 chapters, and we can come back to the z-score right here. We'll come back to this little guy right here. And we're going to start continuing those statistics. Okay, that's what I got for 2.5. We are done. And please tell me it was recording. It was not recording, huh? It was recording. It was recording. Yes, it was. Okay. I'm going to end it right now.